You ready? I'll let you go.
All right, so I'm Stephen Weinmann, and I'll be giving a talk about one of my research topics. And so we know water scarcity is a huge issue across the world, and we can quantify that with approximately 2 billion people lack access to clean water sources. Well, membranes are a tool that we can help use to provide clean water for these people. However, when you clean that water, you're bringing all this bad stuff near the membrane surface, and at some points, they like to attach what's known as fouling the membrane. And so specifically, one of the things I'm interested in is biofouling. And biofouling is where you have biomolecules, proteins, bacteria, things like that attached to the membrane surface. And when they do that, you lose productivity over time, you lose your salt rejection over time, and so this is not good. So then you have to clean the membrane, but after so many cleanings, you have to replace the membrane because these cleanings are detrimental to the membrane itself. So we need to help solve this problem such that we can make the membrane more viable for all these other places that need water. And so to do that, we have to understand the mechanism of biofouling. And you have a base substrate, which you would think is our membrane here. We have a conditioning film that gets applied to the surface. You can think of that as biomolecules and proteins. The bacteria then absorb to that conditioning film and grow into a biofilm. Well, our thought process was, let's eliminate this conditioning film. We might be able to eliminate everything else. And so there's two primary methods in the literature that have been used to do this. One is through a chemical coating. You can think of neutral charged molecules that are PEG-based, or zwitterions that are polyelectrolytes. And what they do is they reduce the amount of fouling that occurs, but they also enhance the cleanability. Or you can think of a more recent area, which is through physical patterning. You pattern the membrane surface, you change the surface hydrodynamics, the fluid hydrodynamics right at the membrane surface, and you can reduce the amount of fouling that occurs. So our thought process was, let's take these two methods that have been researched and combine them into one and see if we can produce a better membrane than either method alone. And so we can do that through applying a stamp and then a chemical coating, and this has all been done on a piperazine-based polyamide membrane. So how we do this is through a simple two-step process. We stamp the membrane with a stamp that we just purchased from a company, and then we do a simple PEG-based chemistry on top of that. Pretty easy. We publish this if you want more detail. I'm going to talk about 3 different types of membranes that we looked at. One is a reaction-only membrane where we only do the chemical modification. One is where we do the patterning process but with a flat wafer as a control, and this is called pressed. And then we have another one where we actually pattern the membrane, this is called pattern. So just to show, here's an AFM image that we actually patterned these membranes. And then to show we did the chemical reaction by adding different weight percents of our modification layer, we've reduced the contact angle, our reaction is successful. So to make sure that we haven't damaged these membrane surfaces, we looked at salt, flux, and rejection studies. And so if you look at the flux across each individual bank here, you see statistically there's no difference. We haven't ruined the flux at all. We do have a slight flux decline across these two. We've added a new modification layer to the surface. We've reduced, or we've increased the resistance, mass transfer resistance to flow through the membrane. So this is expected. If we look at the rejection, which is another big deal, you can see with magnesium sulfate, we really haven't done much anything to this. And then when you look at a multiple mean hypothesis test at 95% confidence, statistically there's no difference between these. So we haven't damaged the membrane surface at all. We can move to fouling studies. We look at sodium alginate, which is a model biomolecule for foulants. If you look, we had chemical modification layer. You can see we've significantly enhanced the amount of fouling reduction that occurs. And then when we press the membrane, statistically no difference. At 0.8%, we did increase or reduce the amount of fouling that occurs. That's due to drastically reducing the surface roughness of the membrane, and surface roughness directly correlates to the amount of fouling that occurs. So then when we pattern the membranes, you can see statistically there is no difference between these two, but if you look at just the purple squares here, this is the modification layer with patterning, you can see that there's essentially no flux decline. Now this is only over 2 hours. You can imagine you want to run these for a lot longer. So we believe if you started to run these for a lot longer, these differences would start to become significantly different. And so that is where we're headed towards in the future. I'd like to acknowledge my advisor, Dr. Houston, and my lab mates and my funding sources. Thank you.